This animal is not a dinosaur. It lived before dinosaurs existed, and yet, in a strange way, it is closer to us than to them. Its name is Dimetrodon. With a long skull, powerful jaws, sharp teeth, and a tall sail rising from its back, Dimetrodon looks like something from the age of dinosaurs. But it walked the Earth tens of millions of years before the first dinosaur appeared. It belonged to a different dynasty. A dynasty that ruled the land before dinosaurs, the synapsids. These were not reptiles in the modern sense. They were the ancient relatives of mammals. Their descendants, after many transformations, would eventually lead to us. So, when we look at Dimetrodon, we are not looking at a failed dinosaur. We are looking at a distant branch of our own deep history. This is the story of the Permian Period, the world before dinosaurs, when mammal relatives ruled the land, deserts expanded across a supercontinent. Strange herbivores fed among seed plants, saber-toothed predators hunted in dusty landscapes, and the greatest extinction in Earth history nearly erased complex life from the planet. The Permian began about 299 million years ago and ended about 252 million years ago. It was the final chapter of the Paleozoic era, and it ended in catastrophe. But before the fire, before the poisoned oceans, before the silence of the great dying, the Permian was full of life. Not dinosaur life. Something older, something stranger, something closer to us than we expect. To understand the Permian, we should not begin with rocks. We should begin with rulers. The rulers of this world were not tyrannosaurs, not sauropods, not raptors, not horned dinosaurs. Dinosaurs were still in the future. The most important land animals of the Permian were often synapsids, the mammal line amniotes. This is a crucial idea. Life on land had already split into major evolutionary branches. One branch, the sauropsid line, would eventually lead to reptiles, dinosaurs, pterosaurs, crocodilians, and birds. The other branch, the synapsid line, would eventually lead to mammals. The Permian was the great early age of that synapsid branch. It was the age when our distant relatives became predators, herbivores, giants, hunters, survivors, and victims. In the early Permian, animals like Dimetrodon occupied top predator roles in many ecosystems. Nearby, herbivorous synapsids such as Edaphosaurus fed on plant material. Both animals had large sails on their backs, but they lived different lives. Dimetrodon was a hunter. Edaphosaurus was a plant eater. Together, they show us something important. By the early Permian, land ecosystems were no longer simple. There were already predator and prey relationships, herbivore niches, territorial competition, and specialized body plans. This was a real terrestrial world. But it was not yet the world of dinosaurs. It was the world of mammal relatives before mammals, and it was built on one of evolution's most important inventions: the ability to reproduce away from water. Long before the Permian, vertebrates came from water. Their ancestors were fish. Then in the Devonian and Carboniferous, some of those fish-like animals began to move onto land. They developed limbs, digits, stronger skeletons, and lungs. But early land vertebrates still carried a weakness. They could walk on land, but many of them were still tied to water. Their eggs were soft and vulnerable. Their young often needed aquatic environments. Their skin and reproduction kept them close to ponds, swamps, rivers, and wet forests. In the Carboniferous period, this was not a major problem. The world was full of wetlands. Equatorial regions were covered with vast coal-forming forests. Amphibian-like animals could thrive because water was everywhere. Swamps were not obstacles. They were empires. But the Permian changed the rules. As the Carboniferous world gave way to the Permian, many regions became drier and more seasonal. The great coal swamp habitats declined in many places. The land was becoming more open, more continental, and more difficult. For animals still dependent on water, this was a challenge. For amniotes, it was an opportunity. The amniotic egg was one of the great evolutionary breakthroughs of life on land. Inside the egg, protective membranes surrounded the embryo. In a sense, the animal carried a small private water world around its developing young. This meant that reproduction no longer had to happen in open water. Amniotes could move farther from ponds. They could explore drier forests, river margins, uplands, and semi-arid landscapes. They could build a new kind of vertebrate world. Synapsids were one branch of these amniotes, and in the Permian they began to rise. This is why Dimetrodon matters. It was not just a strange predator with a sail. It was part of a much larger transformation. The shift from swamp-bound life to dryland dominance. The Permian was the age when vertebrates truly began to conquer the interior of the land. To understand the Permian animals, we must understand the world beneath their feet. By the Permian, Earth's continents were moving together into one enormous supercontinent, Pangea. Imagine almost all major landmasses joined into a single vast body of land, stretching from pole to pole. Around it lay the immense ocean Panthalassa. Along one side opened the ancient Tethys Ocean. This geography changed everything. When continents are separated, coastlines are abundant. Moisture from the oceans can reach far inland. But when land is joined into one giant supercontinent, much of the interior lies far from the sea. Rain becomes limited. Seasons become stronger. Temperature extremes become greater. The center of Pangea became a place of dry winds, seasonal drought, and expanding deserts. The Permian was not one uniform desert. There were still rivers, floodplains, coastal areas, forests, wetlands, and marine basins. But compared with the Carboniferous, many terrestrial environments were becoming drier and harsher. This was the stage on which synapsids evolved. Dimetrodon did not simply appear because evolution wanted a monster. It appeared because the world had created a niche. Large terrestrial predators were now possible. Herbivorous amniotes were expanding. Food webs were becoming more complex. The swamp was no longer the center of everything. The land itself was opening, and life moved into it. But every opening creates a test. The animals of the Permian had to deal with heat, drought, seasonal food, and changing vegetation. The winners were not always the strongest. They were the ones whose bodies matched the new rules. Dimetrodon is one of the most recognizable animals of the Permian, and also one of the most misunderstood. For decades, it has appeared in books and toys beside dinosaurs, as if it belonged to the same age. But Dimetrodon lived mostly in the early Permian, long before the first dinosaurs of the Triassic. It was a synapsid, a member of the mammal line. Its skull was long and deep. Its jaws carried teeth of different shapes. At the front were larger canines, while other teeth were adapted for cutting and gripping. Its body was low and sprawling compared with later mammals, but it was an efficient predator for its time. And then there was the sail. The sail of Dimetrodon was supported by tall neural spines extending from the vertebrae. For a long time, scientists suggested It may have helped with thermoregulation, warming the animal in the morning or releasing heat later. That may still be part of the story, but the sail may also have been used for display, species recognition, or sexual signaling. The truth is probably complex. Evolution rarely builds structures for only one purpose. In the same world lived Edaphosaurus, another sail-backed synapsid. But unlike Dimetrodon, Edaphosaurus was herbivorous. Its skull was smaller, its body more barrel-shaped, and its teeth were adapted for processing plant material. This is important. The sail-backed body plan was not limited to predators. In the early Permian, synapsids were experimenting with form, function, metabolism, display, diet, and habitat. Dimetrodon and Edaphosaurus were not primitive monsters waiting for dinosaurs to replace them. They were successful animals in their own world, a world where the mammal line was already writing its first empire. But that world would not stay the same. The Permian still had another revolution waiting. Every animal world is built on plants. Predators may dominate our imagination, but ecosystems begin with sunlight. In the Carboniferous, vast swamp forests had stored huge amounts of carbon. Giant lycopsid trees, horsetail relatives, and seed ferns grew in wet lowlands. Their remains became peat, then coal. But in the Permian, many of those wet coal forests declined, especially in regions that became drier and more seasonal. New plant communities became more important. Seed plants spread across many landscapes. Conifer-like trees, seed ferns, cycads, ginkgo-like plants, and other gymnosperm groups occupied habitats that were less dependent on constant swampy conditions. In the southern supercontinent, Gondwana, one plant became especially famous: Glossopteris. Glossopteris was a seed fern-like plant with tongue-shaped leaves. Its fossils are found across lands that are now separated by oceans: India, South Africa, Australia, Antarctica, and South America. These fossils later became one of the important clues that these continents had once been connected. For an Indian audience, this part of the Permian is especially close. The Gondwana rocks of India preserve coal-bearing formations and plant fossils linked to this ancient southern world. The land that would one day become India was not yet in its modern position. It was part of Gondwana, carrying forests and ecosystems very different from modern India. These plants were not just background, they changed animal evolution. Tougher, drier adapted vegetation created new food sources. Herbivores needed stronger jaws, beaks, grinding surfaces, fermentation, and digestive strategies. As herbivores became more successful, predators had more prey. The Permian food web grew from the ground upward. First, the plants changed. Then the herbivores changed. Then the predators changed. Evolution is not a ladder. It is a web. And in the Permian, that web was becoming more terrestrial than ever before. As the Permian continued, the early sail-backed synapsid world began to change. The pelycosaurs, including Dimetrodon and Edaphosaurus, were important in the early Permian. But later, a more advanced group of synapsids rose to prominence. They were the Therapsids. Therapsids were still not mammals. But they were closer to mammals than Dimetrodon was. And in their bodies, we begin to see the first hints of the mammalian future. Their limbs became more upright compared with earlier sprawling forms. This allowed more efficient movement. Their jaws became more powerful and specialized. Their teeth became more differentiated, with different shapes for different functions. In many reptiles, teeth are often relatively similar along the jaw, but in the synapsid line, teeth began to specialize. Canines, incisors, and post-canine teeth started to develop different roles. This matters because differentiated teeth are one of the great signatures of mammals. We do not simply bite, we cut, pierce, crush, and grind. That story begins deep in synapsid evolution. Some therapsids may also have had higher metabolic rates than earlier amniotes. Some later forms may have had insulation or hair-like coverings, though evidence varies depending on the group and time. But the direction is clear. Therapsids were becoming more active, more specialized, and more mammal-like. The Permian was not just producing strange, extinct animals. It was quietly shaping the architecture of our own bodies. Jaw, teeth, posture, metabolism, survival on land. The mammalian story did not begin with tiny shrew-like creatures hiding from dinosaurs. It began much earlier in the Permian, when our distant relatives were among the dominant animals on Earth. A world of predators needs a world of prey. And in the Permian, one of the most successful herbivore groups was the Dicynodonts. Dicynodonts were therapsids. They belonged to the mammal line, but they looked unlike any modern mammal. Many had stocky bodies, strong limbs, short tails, beak-like mouths, and in many species a pair of tusks. The name Dicynodont means two dog teeth, referring to those tusk-like canines. They were plant eaters. Their beaks helped them crop vegetation. Their bodies were built for processing plant material. Some were small, others became large and heavily built. In many late Permian ecosystems, Dicynodonts were among the most common and important herbivores. They were not beautiful in the way people often imagine prehistoric animals. But evolution does not care about beauty, it cares about function. A strong body, a useful beak, a reproductive system suited for land, a way to survive seasonal environments, a way to turn plants into flesh. That was enough. Dicynodonts show us that the Permian was not only a world of predators, it was a world of herbivore success. Herds may have moved through dry woodlands and floodplains, feeding on low vegetation, seed plants, and tough plant material. Where Dicynodonts gathered, predators followed. Their existence helped support the next great Permian drama, the rise of saber-toothed hunters before mammals. Long before saber-toothed cats evolved, evolution had already tested the saber-toothed design. In the late Permian, some of the most fearsome predators on land were the gorgonopsids. They were therapsids, part of the mammal line. And they were among the apex predators of their time. A gorgonopsian's skull is difficult to forget. Long, deep, powerful, armed with enlarged canine teeth. These animals were not cats, not reptiles, not dinosaurs. They were something older, a vanished experiment in predatory synapsid evolution. Their saber-like canines were designed to deliver deep, devastating bites. Their prey may have included Dicynodonts, Periosaurs, smaller therapsids, and other Permian vertebrates. Imagine a dusty late Permian floodplain. A group of Dicynodonts feeds near sparse vegetation. The air is dry, the light is harsh. The world is quiet except for insects, wind, and the low movement of animals. Then from behind cover, a gorgonopsian appears. It is not fast like a modern cheetah. It is not intelligent like a wolf. It is not a dinosaurian predator. It is a different kind of hunter from a different Earth. But in that world, it is enough. The late Permian was in many places a synapsid world. Herbivorous synapsids fed among the plants. Carnivorous synapsids hunted them. Small cynodonts moved through shadows. Long before mammals became dominant, the mammal line had already ruled. And then, almost all of it would be taken away. When we tell prehistoric stories, we often focus on giants. But survival often belongs to the small. Among the late Permian Therapsids were animals called cynodonts. Cynodonts were more mammal-like than many earlier Therapsids. Their jaws and teeth were more advanced. Their posture was changing. Their skull anatomy carried features that pointed toward the later evolution of mammals. They were not yet true mammals, but they were close to the road that would eventually lead there. Many cynodonts were small, perhaps living in burrows, feeding on insects, small vertebrates, or other food sources depending on the species. In a world dominated by larger herbivores and predators, they may not have looked important. But deep time often hides the future in small bodies. The giant rulers of an age can vanish. The overlooked survivors can inherit tomorrow. The cynodonts are important because some of them survived the end Permian extinction and continued into the Triassic. From later cynodonts, true mammals would eventually evolve. So, while Dimetrodon captures our attention and gorgonopsids dominate the imagination, the most important survivors may have been smaller, quieter animals, not rulers, not giants, but carriers of the future. This is one of the great ironies of evolution. The animals that define an age are not always the animals that survive it. The Permian was not only a synapsid story, other life continued around them. Reptile-line amniotes were diversifying. Some were small, fast insectivores. Others explored new ecological roles. Although dinosaurs had not yet appeared, the reptile line branch was quietly evolving in the background. Amphibian-like animals also survived, especially near rivers, lakes, and wetlands. They no longer ruled the land as they had in the Carboniferous, but they remained important in aquatic and semi-aquatic environments. And beyond the land, the seas were full of life. The Permian oceans still carried the character of the old Paleozoic world. Brachiopods filtered food from the water. Crinoids rose from the sea floor like living flowers. Bryozoans formed colonies. Corals built reef structures. Ammonoids swam through open water. Sharks and bony fishes moved through marine food webs. And trilobites, ancient survivors from the Cambrian, still existed. By the Permian, trilobites had already passed through hundreds of millions of years of evolution. They had survived multiple crises. They were among the great endurance stories of animal life. But even their long history would not save them from what was coming. The Permian Sea was rich, but vulnerable. Large parts of marine life depended on stable oxygen levels, chemistry, temperature, and shallow habitats. When those conditions changed, the sea would become one of the main theaters of extinction. The land had its rulers. The sea had its ancient survivors. Both were approaching the same catastrophe. By the late Permian, life had adapted to a difficult world. But adaptation is always local. It fits an organism to the world as it exists. If the world changes too quickly, yesterday's advantage can become tomorrow's weakness. Pangea created extremes. Continental interiors were dry and seasonal. Some ecosystems were already under stress. Sea levels shifted. Marine environments became vulnerable. Food webs were complex, but complexity can also create fragility. On land, animals had evolved into specialized roles. Dicynodonts as herbivores, gorgonopsids as apex predators, cynodonts as small survivors in the shadows, reptile-line amniotes exploring other niches, amphibians holding near water. In the sea, entire communities depended on oxygenated water, stable temperatures, and carbonate chemistry. The world was alive, But it was not invincible. Then, in what is now Siberia, the Earth began to open. Near the end of the Permian, one of the largest volcanic events in Earth history began: the Siberian traps. These were not ordinary volcanic eruptions. They were flood basalt eruptions, enormous outpourings of lava that covered vast areas. Lava spread across the land in repeated flows, but the lava itself was only part of the danger. The real catastrophe came from what the eruptions released: carbon dioxide, sulfur gases, volatile compounds, greenhouse gases from magma interacting with buried sediments. The atmosphere changed, global temperatures rose. Acid rain may have damaged land ecosystems. Oceans absorbed carbon dioxide and became more acidic. Warming oceans held less oxygen. In some regions, marine waters became anoxic, starved of oxygen. Toxic conditions may have spread. Food webs began to fail. This was not a single explosion that killed the world in one dramatic moment. It was a long environmental crisis, a planet changing faster than life could adapt. For millions of years, the animals of the Permian had been shaped by their world. Now that world was turning against them. The end of the Permian was the greatest mass extinction known in Earth history. It was so severe that it is often called the Great Dying. In the oceans, the losses were catastrophic. Most marine species vanished. Reefs collapsed. Many brachiopods, crinoids, bryozoans, ammonoids and other groups suffered enormous losses. Trilobites disappeared forever. After surviving for more than 250 million years, after passing through earlier crises, after witnessing the rise of fishes, forests, insects and land vertebrates, trilobites ended at the Permian boundary. On land, the catastrophe was also severe. Many Therapsid lineages vanished, gorgonopsids disappeared, large predators and herbivores were devastated. Insects suffered major losses. Plant communities were disrupted. The Permian world did not end as one animal falling. It ended as connections breaking. Plants failed. Herbivores declined. Predators lost prey. Oceans lost oxygen. Reefs collapsed. Food chains unraveled. Extinction is not only death, it is the failure of relationships. A predator is linked to prey. A herbivore is linked to plants. A reef is linked to water chemistry. A forest is linked to climate. A species is linked to the world that allows it to exist. At the end of the Permian, those links were broken on a planetary scale. The rulers before dinosaurs were gone. The old Paleozoic seas were shattered. The world entered silence. But extinction is never complete. Some life survived. Certain dicynodonts survived into the Triassic. Some cynodonts survived. Amphibians survived. Reptile-line animals survived. Marine organisms survived in reduced, wounded communities. The survivors were not always the largest or most powerful. The gorgonopsids did not survive. Many great herbivores did not survive. Entire marine lineages disappeared. But some smaller, more adaptable animals passed through the narrow gate. In the early Triassic, ecosystems were damaged and unstable. Recovery took millions of years. The world after the Great Dying was not immediately full of dinosaurs. It was a wounded planet, slowly rebuilding. But in that broken world, new opportunities appeared. Archosaur-line reptiles would eventually give rise to crocodile relatives, pterosaurs, and dinosaurs. Cynodonts would continue along the path toward mammals. The Triassic did not begin as a triumph. It began as survival. The dinosaurs would rise later, not because they had always been destined to rule, but because the Permian extinction had cleared the stage. Before dinosaurs, synapsids ruled. After the Great Dying, the rules changed again. The Permian was an age of strange greatness. It was the age of Dimetrodon, the sail-backed predator that was not a dinosaur. It was the age of Edaphosaurus, the sail-backed herbivore. It was the age of Therapsids, the mammal-line animals that began to transform teeth, jaws, posture, and metabolism. It was the age of Dicynodonts, tusked herbivores that fed across dry landscapes. It was the age of gorgonopsids, saber-toothed hunters before mammals. It was the age of small cynodonts carrying the future quietly through disaster. And it was the age of Pangea, a supercontinent that changed climate, vegetation, habitats, and the destiny of life on land. The Permian teaches us that the history of life is not a straight line toward the present. It is a series of worlds. Each world has its rulers. Each world has its rules. And each world feels permanent to the creatures living inside it. The synapsids ruled before dinosaurs. The Paleozoic seas flourished before the Mesozoic. The forests and reefs and predators and herbivores all belonged to a world that seemed complete. Then the planet changed, and almost everything ended. But from the ashes came survivors. Small animals in burrows, scattered lineages in damaged forests, marine survivors in altered seas, cynodonts carrying the deep future of mammals, reptile-line survivors carrying the future of dinosaurs. The Permian was not only the end of the Paleozoic, it was the great reset before the age of dinosaurs. And hidden inside that devastation was a strange truth. Life does not continue because it is dominant. It continues because something survives. Not always the strongest, not always the largest, not always the ruler. Sometimes the future belongs to the small creature in the shadow, waiting for the world to begin again. The Permian was the forgotten empire before dinosaurs, and the great dying was the fire through which the next world was born.